Welcome to this webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. Welcome also to folks from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster and I'm chairman of the Anglian Coastal IET Local Network, and I'll be your host for this evening. I'm delighted to introduce our speaker, Mr. Gavin Young. Gavin is responsible within the Vodafone Group for fixed broadband access, technology strategy, architecture, vendor roadmaps and standards across the 17 countries where Vodafone currently has fixed access assets. This encompasses fiber, cable, DSL access technologies, together with the associated fixed mobile convergence and virtualization aspects. Now, COVID-19 lockdown has highlighted just how critical the performance of our home broadband is to enable us to work, to attend school, to socialize, and to entertain ourselves. Speed is necessary, but it is not sufficient. Gavin will explain how the recently standardized technique of quality attenuation can be used to give much deeper insights into network performance so that networks can meet the challenges of today's and tomorrow's even more demanding applications. Gavin, over to you.
And thanks for the kind invitation to come along this evening and talk to you about quality attenuation for broadband performance measurement. What I'm going to cover this evening is the motivation. Why did we look into this technique called quality attenuation? What was our incentive? So I'll set a bit of context and then I'll give you a bit of a brief overview of what quality introduction is, and then talk about its use, various use cases, how we put it to help us in our deployment of broadband services, and then we'll wrap up. So in terms of motivation, why do we need a quality framework? For years, the broadband industry has been very focused on speed. I think one of the easiest jobs for the last 10 years has got to have been broadband marketing. My number's bigger than yours, so it must be better. And now I'll go back to the golf course. So we've had this focus on quantity of bandwidth for a long time now, since the evolution from voice band modems to ISDN to the early days of broadband on ADSL and early cable modems, and now much more fiber-rich services. And that served us pretty well at first. Every time we increased speed, it made a difference to application performance, application outcomes, which is what customers really care about. But we're now reaching a point of diminishing returns, as we'll talk about in a moment. So when you look at broadband, the initial focus is quantity of bandwidth, how much. But there's also, the kind of capability of that bandwidth, and by that I mean, what can you do with that bandwidth, that broadband connection? So we've done a lot of work around functionality, supporting synchronization techniques for things like small cell and mobile backhaul, and that's standard in a lot of vendor equipment now. So that increases the utility of broadband connections. But really, what we're focused on this evening is the quality. How good is that broadband connection? And this brings into play different attributes like latency, consistency, stability, stationarity, and reliability. And I think many of us who have been reliant on our broadband connections for perhaps 15 hours a day during lockdown, for work, for school, and for socializing and entertainment, as Kevin mentioned in the introduction. I think when you're using something for that amount of time, if there are any problems with quality, you tend to become aware of them. But if we can get that right, that radically increases the utility of broadband. So if we look at the business model on a page of a broadband network operator, if we start at the bottom left there, network operators invest to build networks. They build out coverage, but also a key ongoing investment is capacity and bandwidth, making those networks faster to cope with, not just more customers, but new and demanding services. So that's the fundamental investment. But what customers really use those networks for is to connect and deliver applications, and it's the application outcome that is important. And there are ways of testing that. Some are application specific, ways of measuring voice quality or video quality on networks. There are some generic approaches, and some applications, things like web page load time, are important for surfing. But typically the main way a customer tests their own broadband connection is via a speed test. And generally, if they get the number they expect, hopefully, if you get that right as a network operator, they're happy. And that customer experience is measured in a variety of ways. Things like NPS is Net Promoter Score, and customer satisfaction surveys, and churn rate, where customers vote with their feet whether they stay with you or not. So that's typically the business model. And if you get that right, the outcome at the top right there is hopefully a happy customer that you can upsell them to new services, increase your average revenue per user. But if you get that wrong, then that will generate support calls and customer churn when you lose customers to competition. So that's been a very simplistic model. Invest in bandwidth, create better speeds. That in the early days certainly created better application outcomes, and then if you get that right, you have happy customers. The issue now is that we're actually in the era where we're capable of providing and selling more bandwidth to our customers than they perhaps actually need today. So via fiber and cable DOCSIS technologies, we've got a lot of customers we're providing gigabit per second broadband speed to, which is great. And applications are evolving. But where do you go from there? You can't stay on this speed treadmill if it doesn't make a noticeable difference to the application outcome to a customer. So, for example, if you're watching an ultra high definition Netflix 4K on your fancy new TV, that might need around 25, 30 megabits per second to deliver that. You may have 3 or 4 people in the house doing that independently. If you've got unsociable teenagers and they want to be in their own room doing that, then maybe you can multiply that by 3 or 4 times. But all of that fits easily within a 1 gigabit per second connection. If you then go to that customer and you upgrade their broadband speed from 1 gigabit to say 2 gigabit per second, it's not going to make their Netflix look any better. So that's the issue that we're now as an industry in potentially diminishing returns, and so this obsession just focusing on speed is not going to withstand scrutiny. We need to focus on other aspects of improving the quality of that connection, and not just assume that making the connection faster will do the job. And to be honest, it's not a great business to be in if you continually invest in bandwidth. If your customers don't notice any difference, they're not going to value that investment. They're not going to want you to pay you more for it, and therefore that's a pretty lousy business model. Okay, so let's take a look now at the end-to-end digital supply chain in a broadband connection. So on the left at the top there, we have end user devices in your home, PCs, laptops, mobile phones connected via Wi-Fi. Connect your broadband router, goes over the access network to backhaul and transport and core networks, and ultimately, typically to some kind of application or content server on the internet. And if you just focus on the kind of broadband access speed, that's only really affecting that access link there, and not necessarily all the other elements in the chain. So, and it's the end-to-end connectivity, including the Wi-Fi, vitally important these days, that influence how well an application will perform. So if we look at, say, a downstream packet flow from an application or content server on the right, all the way to the end user device consuming that content, then those packets, as they traverse the various hops, there's only 2 things that can happen to them. They will get delayed, and some of them may get dropped. So that represents, the kind of quality of the packet delivery, that in an absolutely perfect world, the perfect network outcome would be 0 delay and 0 loss. But those packets don't appear instantaneously, and they don't always all get there. So sometimes this quality attenuation measurement we'll talk about is called delta Q. It's the delta, the gap between perfection, 0 delay and 0 loss, and the reality of finite delay and finite loss. So you start off with perfect quality, but then as the packets go towards the customer and are consumed, there is a degradation from that. And that can be caused by a variety of things, whether it's Wi-Fi issues, congestion, the broadband router performance, capacity issues, rerouting, fiber problems, applications moving around servers can change delays and things as well. Now, I just talked about quality of broadband, and I talked about latency, delay, and I talked about packet loss. But some folks might think, well, it surely isn't broadband quality all about, just broadband speed and throughput. Well, actually, they're related. If you look at there's 2 degrees of freedom in this balance between the load on the network, the loss the packets experience, and the delay they experience. So sometimes when we talk about insufficient bandwidth, what that really means is at the offered load onto that network, the resulting packet loss and delay exceeds the acceptable performance bounds of the user application. So bandwidth is necessary but not sufficient. So as I said earlier, for something like 4K Netflix, you might need 25, 30 megabits. But if there are other applications and things loading that bandwidth, and the overall load on that pipe is excessive, then that can result in packet loss and delay that eventually apart from the fact Netflix can rate adapt down, but ultimately you reach a point where maybe the packet loss or whatever is unacceptable. So you've got these kind of 2 degrees of freedom. So loss and delay and kind of bandwidth are not completely independent things. There is a link between them. And the other point to note is that we tend to talk about bandwidth sometimes as a fungible quality, a kind of a commodity that you can trade and use in different scenarios. But actually, not all bandwidth is created equal. So if we look at queuing and buffering, for example, if you have 50 megabits per second on an empty network, that is not the same as 50 megabits per second on a loaded network. Where the packet flow is competing with other traffic, and that can get queued up and delayed. And similarly, 50 megabits per second on a 100 megabits per second Ethernet port is not the same as 50 megabits per second on a 10 gigabit per second port, because the rate that the packets are clocked out of that that serialization delay is different. And similarly, 1/10 of 100 megabits per second is not the same as 10 megabits per second in terms of the rate the packets are clocked. And finally, physical layer consistency varies. So 50 megabits per second on a DOCSIS 3.1 network is not the same as 50 megabits per second on a 4G or a GPON network. The physical layer characteristics and the bit error rate and the bit errors and the way they then manifest themselves in the packet layer as maybe clusters or bursts of errors or whatever is very different. That depends on the physical layer. So, as I say, bandwidth is not a fungible commodity. And so we have to ask ourselves, is actually bandwidth, just using bandwidth, is that the wrong measure? We've used bandwidth as a proxy for a good application outcome. And in the early days of broadband and data transmission, that was very much the case. As we increase the speed of broadband links from 500 kilobits per second to 2 megabits to 10, to 100, all those steps made an increase in an improvement in, for example, your ability to surf the web. But then you reach a point where it is diminishing returns, and things like latency and round trip time of how the way protocols operate become the limiting factors, and protocols like TCP, for example. So when we were looking at different ways of assessing quality of network, so as I say, there's a link between bandwidth and delay and latency, etc. And there's an abundance of techniques and standards for measuring that today. And some of these techniques, they give you a minimum, an average, and a maximum round trip time. So RTT is round trip time, and you can gather various statistics. And it gives you some kind of parameters, but really we wanted something that was going to give us a much deeper insight. And we wanted a high fidelity measurement approach, something more akin to an X-ray of the network, to not just look at latency, but look inside latency and dissect it and understand the root causes and the various elements. And we wanted to, not just measure it, but get into those constituent components. And that's where we came across the quality model and quality attenuation approach. And if we compare the bandwidth approach to the world of broadband and the quality approach, they're very different. So the bandwidth model, it's a scalar. It's megabits per second or gigabits per second, which in itself is actually an average. It's per second, very simplistic, down to a single number. It is understood by customers today. As I said, my broadband's bigger than yours, my number's bigger than yours, so it must be better. Quite simple to get your head around. The logical extension of the bandwidth model is the perfection is infinite bandwidth. How do you make it better and better? You increase that bandwidth forever. If you look at the quality model, that's more complex. It's an N2 It's got multiple dimensions to it that could encompass packet loss and latency and the consistency and predictability of those and reliability, etc. Before the Broadband Forum did some work on this, there wasn't really much in the way of a well-documented standard and definition around some of these aspects. And you also need to think about the units of supply and demand. But one of the key things is the logical extension to perfection is zero defects, which might sound familiar from manufacturing type approaches. But in the broadband context or the networking context, zero defects is zero packet loss and zero delay. And from an engineering perspective, when you're trying to measure these things and compare yourself to perfection and where you'd like to be, it's a lot easier to measure how close you are to zero than it is to measure how close you are to infinity. So certainly the quality model, while it might be a little bit more complicated to get your head around, is certainly mathematically more tractable in many areas of analysis. So that's the motivation and the context and the introduction. Let's look at quality attenuation itself and an introduction to that. So if I look at an approach where I send a stream of packets, a low rate stream over a broadband connection, with various sizes of packets, a range of sizes, and the timestamps, and I just plot the observe time, the delay, one-way delay between measurement points over time, then I get this kind of fuzzy kind of path on the left. That's the raw data, that end-to-end delay. If I then want to examine those as a probability distribution, it gives a I can plot them as relative frequency versus the observed delay as shown on the right there. And you get a couple of artifacts from that. You get a lower bound and an upper bound and a kind of shape. So, it gives some insight, but it's of limited use for actually measuring performance. But if I then sort those measurements and plot the observed delay against the packet size, that range of packet sizes, then suddenly you get a structure, a clear structure emerging. This defined line with a defined gradient and thickness, etc. And this is at the heart of the quality attenuation measurement approach. You send this stream of packets of various sizes and timestamp, and then you can sort them like this. And it turns out that if you have that plot of your delay versus the size of the packets, then there are three characteristics of that graph. One is the intercept, one is the gradient, and one is the thickness of the line. And it turns out, and I'll give you a reference later, the Broadband Forum work on it, but those three characteristics of the graph relate to three sources of latency in that measurement. So the intercept point is effectively the transit time of a hypothetical zero length packet, and that's due to the geographic and delay, the physical distance and the speed of light of that connection. And that's, if you want to improve that component of the latency, that's where things like using caches or CDNs to move content closer to the customer to reduce that geographic distance, or things like MEC, which is multi-axis edge compute, moving the compute power from a remote cloud data center to perhaps an edge cloud, closer to the customer. That will reduce that G component in performance. The second one there is the S component, is the serialization delay, and this is related to the bandwidth or the interface speed of the network boxes clocking those packets in and out across links. So if you do what's been typical in networking over the years, is to kind of throw bandwidth at the problem and upgrade a link speed, it's that S component is the only component you're really affecting by that. And you'll see, you know, in a network where that's been done, you've got very high speed link, the S component is a lot less, so it actually looks a lot flatter than having a defined gradient there. And then finally, we've got the thickness of the line there, and that is due to the variable delay, or which is down to queuing and buffering. And we talk a little bit more about buffers and things later. But this is where, you know, under load, if the network is not empty, then packets get queued as they hop across the links to different equipment, and that queuing and that scheduling and buffering is what, you know, results in that V component. So the beauty of quality attenuation is we can kind of dissect this delay into these three components, and also we can separate them between upstream and downstream. So instead of a single metric of a round trip time, we now have 6 separate components, 3 upstream and 3 downstream. And these are, and particularly for the V component, these are not scalars. We gather these as statistical distributions. And that gives us a much greater insight into the network performance. And we measure this with, you know, a simple, you know, packet generator generating packets of different sizes with those timestamps. We note the timestamp as packets are clocked in and out of equipment, and that is then can be captured for analysis later, and then, you know, post-processed or perhaps even in real time to extract various metrics as we've shown just now. So that's the principles of how quality attenuation works. Let's have a look at what can you actually use this for. Well, some of the things that we've observed by using quality attenuation is first of all rerouting events. We're doing some measurements of comparing VDSL and fiber and 4G lines in one of our country's networks, characterizing the different technologies, and we'll show a few results from that in a moment. But sometimes you'll see a step function where you've basically, you know, increased the G component, because you might have, for example, diverse routes through a core network or an international network, and packets, you know, can be rerouted and take a different path. Or it might be a kind of ring network where there's an east or west option, or traffic goes a different way around the ring, and you can get these step functions there. Similarly, load balancing effects, packet fragmentation, that's a classic one. You see a discontinuity when you plot those, the delay versus the packet length, and you can see fragmentation effects. You can see, you know, rate adaptation and dynamic line management effects, changing speed profiles, and on radio networks as well. And sometimes if you have a CPE processor that's maxed out, these kind of effects show up. One of the most valuable ones we found is misconfigured schedulers. This is a really subtle problem, really quite hard to find sometimes with traditional tools. And sometimes they can be transient. It only manifests itself under certain traffic patterns or traffic loading conditions that can cause, you know, queue saturation, buffer bloat, and a bunch of issues. So some of those can be quite subtle issues, and it's been really useful to diagnose those. Quality of service benefits, I'll show an example of that in a moment. And, you know, other technology and architecture upgrades we've done before and after measurements, converting a centralized cable network to a distributed architecture, and seeing the before and after differences there. So a range of things you can observe doing this. And we've measured a number of technologies in a number of countries using this technique, where we've had probe locations in customer premises, around the kind of edge of the network, the kind of BNG or CMTS type locations, the edge router, and in the core of the network, and it centralized locations like Amazon Web Services. And measured, you know, the quality attenuation metrics for the various for the hops along there and in each direction. And so just a few simple examples here. So this is just showing the differences between PON, VDSL, and 4G fixed wireless access technologies, where We've got the green is the G component, the blue is the S component, the serialization delay, and then the red and the yellow are the mean and kind of standard deviation of the variable element there. And obviously you see the GPON there with a nice, tight, reasonably consistent performance, and increasing variability as you go from VDSL to 4G. Okay. And one of the main attributes, if you like, of quality attenuation is that it's mathematically composable. That, as I say, you get a statistical distribution for each of these elements of performance of the latency. But the fact that you can combine them and add and subtract them, essentially, you can remove, say, the S and G components from your results and focus purely, for example, on the variable component that I said was due to scheduling. And then you can examine the impact of quality of service markings, for example, on that. So here's an example. This was a PON network in one of my colleagues' lines in Italy, where we absolutely bombarded both the upstream and downstream with video traffic to load up the connection there on the network, and then we turned on quality of service prioritization on his particular PON line. And this is a bit of a dramatic example, but you can see the benefits there. You turn on the QoS and you get lower and more consistent latency of that component, and that's the scheduling doing what it should. So that's just an example there. Now, one analogy, it's a very imperfect analogy when we talk about quality attenuation, but there is a sort of crude analogy with electrical and optical networks in some ways. And this is sometimes helps a few folk understand it if they're less familiar with packet networking. So with electrical transmission, we have electrical discontinuities, impedance mismatches, but before we even get to that point, we have attenuation of the electrical signal over, a connection of metallic bearer. Maybe it's a coaxial cable or a copper pair. Signals get weaker as the signal attenuates. The electrical signal attenuates. Similarly, in optical networks, we start out with a transmit level from a laser, and that optical signal attenuates with distance. And the sort of kind of equivalent in the packet layer is the accumulation of a degradation with distance is the packet latency. The longer the path, the longer the latency. So, as I say, it's a crude analogy there. But if we look at electrical and optical systems, if we have an impedance mismatch or a refractive index mismatch in those systems, then not all of the transmitted power, the electrical power or the optical energy, will make it to the far end. Some of it will get reflected effectively. So that discontinuity causes, a step loss in signal. And in packet networks, you can get a problem where you have mismatched speed. So if you had, for example, a 40 gigabit per second backhaul connection that was then connected into an access link of 1 gigabits per second, then basically you can send packets down. They can burst down that 40 gigabit backhaul, hit the access connection faster than it can empty. it can service them. And we have buffers in packet networks to give us an opportunity to sort of, match speeds a little bit, clock packets in at one speed and then clock them out at another speed. But if you have a mismatch between the buffer size and the maximum burst size from upstream equipment, then that buffer will overflow. So that packet, basically, like an electrical signal that gets reflected, that packet will get dropped. It won't make it all the way to the far end. So, as I say, it's a very crude analogy, but it does help some folks understand the principles of an attenuation type problem with distance and a discontinuity or a mismatch problem that causes some signal loss. So let's look at where we can use this technique in the whole design life cycle, from concept and innovation all the way through to in life. So the natural reaction of most folks is to think, well, I can see how you can use this in life. I can do network health checks. I can do root cause analysis if customers are complaining things aren't quite working. So that's an obvious use case. But you can also use it to compare different design options. As I mentioned earlier, what should be the location of a cache, a Netflix cache, a Google cache, or whatever, or an MEC compute. And with this approach, you can do what-if analysis, you can measure the quality attenuation across the hops, and then you can work out what would be the benefit on application performance of locating a cache or MEC compute at certain points. You can use it potentially in kind of SLA type monitoring. We'll come on to that later. You can certainly use it for design optimization, as I mentioned, things like schedulers. We're doing some work at the moment on a complex convergence kind of capability in the network, and using quality attenuation to fine-tune the scheduling approach used there to maximize the customer experience. But you can also use it to benchmark equipment from different vendors. And previously that might have been physical hardware equipment, but in future that might be a virtual network function. That function running in software. Maybe sometimes different vendors need different NIC cards or interface cards, but comparing different vendors and how well they work is something you can do with this. And this was one of the very earliest techniques of quality attenuation many years ago. It was first used as part of somebody's PhD thesis at CERN, actually, in the high-speed particle accelerator, where they need high-speed data capture, and they were looking to make a decision on some Ethernet switches as part of that measurement system. And so they use quality attenuation to compare different vendor switches and how the performance through the backplane and through scheduling and queuing, etc., and make a decision based on which vendor's box gave the best performance from that quality attenuation perspective, so it wouldn't mess up the measurements. And then you can use it right at the front end of the life cycle in a lab environment for A/B testing, evaluating new technologies and architectures, and so on. So most recently in one of our labs in Berlin, we've been using this to look at the performance of low latency DOCSIS in cable networks and active queue measurement and different techniques like that, and comparing different vendors' CPE and how well they've implemented low latency DOCSIS, and what is the difference in quality attenuation measurement. So extremely useful for that. We've also used this in a lab in the UK, comparing cloud BNG, virtual BNG's virtual network functions implemented in software, and understand how they perform. So lots of different use cases right throughout the life cycle. But one of the most interesting ones I've come across, there's a company in Norway called Domos, who were one of the first to implement the broadband forum capability, and they actually use quality attenuation. They have machine learning in their kind of Wi-Fi expert system, and that machine learning can understand the environment of a Wi-Fi system, the signal strength, the type of device, etc. And that machine learning has now built up an ability to estimate the distribution of latency and potentially loss based on that radio environment and the number of devices, etc. And it can predict that quality attenuation pretty accurately. And if you can predict it, and you also understand the application requirements of the traffic going over that Wi-Fi, then you can dynamically adjust the quality of service markings to certain traffic flows to make sure those that can tolerate a bit of loss or a bit of latency, they're the ones that are assigned the degradation, if you like, and the ones that are less tolerant, get a cleaner path across the Wi-Fi. So that's a very interesting use of quality attenuation to actually couple it with machine learning, predict the degradation, and make sure only the applications that can cope with that degradation are experience it. So extremely interesting approach, and there's a link at the bottom there. And then the final area to touch on is something called quantitative timeliness agreements, QTAs. That is something the Broadband Forum is working on at the moment. So I talked about the coupling between load and loss and delay. In a lot of early work on broadband networks, people realized that latency or delay and packet loss were going to be important to how well an application works. But quite often they set kind of thresholds, simple binary targets. The delay has to be less than this, or the packet loss has to be less than this. Quite simple and not always reflective of the way the application really worked. But if you look at specifying those requirements in the form of, say, 50% of packets need to arrive within 5 seconds, 95% within 10 seconds, 99.9 within 15 seconds or milliseconds, whatever your metric is, and I can have a 0.1% loss rate, then you can actually plot that as this kind of cumulative distribution function. And what that does, it unifies the varying quantity, which is a packet delay, and then the kind of non-event, the packet loss, and you get a uniform approach that you can specify in applications requirements, and you can measure the network and compare the two, and then work out, has the network, has it got the ability to meet the application requirements and deliver the outcome the customer wants. So here's an example here where the requirement is the kind of blue step functions there, and the black is a measured network performance. And in this case, that measured black area is to the left of the requirement, so it's going to meet the requirements and everything's fine. And we've got a couple of examples on the left of how you can express requirements of, say, web page loading or video on demand using this kind of approach. So this is very useful, and if the black line happened to cross the blue line, then you've basically got an application outcome hazard. There's a risk it might not deliver the quality you want, and the degree of mismatch there, and this is what some folks are now been working on, is if they cross, the kind of area under that, if you like, is the degree of badness. So it's like, if you tailor your teenage offspring, you've got to be home by 10 o'clock at night. There's a degree of badness. If they're 1 minute after 10, well, that's not great. But if they're 1 hour after 10 o'clock, then they're in more trouble. And it's that similar concept that mismatch, you can start to quantify that now and work out, how badly you've missed the requirement, and therefore how much of a hazard or a risk you're likely to get. So this is a way of quantifying application requirements using a terminology that is reflected in the network measurement and capability with quality attenuation. So that's an overview there. The vision of where we'd like to get to is to actually have this integrated in network equipment, so that we can measure the quality attenuation, or the delta Q here, across every hop in the network, extract all those components, the three components, upstream and downstream. And if you're able to gather that information, and you can compress this, you can summarize it, you can do hierarchical approaches to make the data storage tractable, but that can give you great insights into either fault finding or optimization of your network. You can do some of this, as I showed in the measurements we've done with separate probes today. You could do this, the customer probe can be a Raspberry Pi or similar. There are separate, servers you could connect into boxes in the network, and we've done that. But where we'd like this to get to is that, network equipment has this inherent capability. And this is entirely possible. A lot of network equipment today has embedded in it a capability, a measurement approach called TWAMP, which is two-way active measurement protocol. That's embedded in equipment, and actually that's already familiar with the concept of timestamps and so on, and with some minor modification that can be used to do quality attenuation measurement. And there's a newer protocol called STAMP, which is simple two-way active measurement protocol. Cable Labs are doing a lot of work on that, and Broadband Forum is working on a draft standard at the moment for how you use STAMP for quality attenuation. And again, that's something that could potentially be embedded in equipment. So instead of having to have separate probes, you can instantiate virtual probes through software as well. So lots of ways to implement this. So in conclusion, I think it's fair to say that bandwidth is necessary for broadband, but it's not sufficient. We need to think about quality as well. But that brings with it some new challenges. As I said, the bandwidth world is very simple. It's been a scalar, a single number. If it's big enough, it's deemed good. With quality, it's a bit harder. So how do we sell the quality of bandwidth and not just the quantity of bandwidth? How do we articulate the improvement you're going to get to application outcomes? And can we have a meaningful quality test instead of just speed tests? But also, what strategies can value and monetize the benefits of better quality? If you're going to invest in this, how can you make money out of that investment, basically? But and finally, how do you market that? What kind of language can you use to talk to customers? Because many won't understand a term like latency. So lots more challenges there from a commercial and business and a marketing perspective. But certainly, what we want to do is get away from the old state of broadband where it was never enough, to now that, having solved a lot of the physical layer issues, can we make it so that it's always sufficient, whatever application you want delivered over your broadband connection, it's always going to work pretty well. And certainly the broadband forum work around quality attenuation and the standards here are definitely a start. So this is the broadband forum work that was published the end of last year, so it's relatively new still, around the measurement architecture and requirements. There is separate work going on at the moment. There's work around there's kind of marketing documents that explain the use cases. There's work going on around those quantitative timeliness agreements that I mentioned, on how you compare application requirements and networks, and there's other technical work on, for example, how you use like the stamp protocol to do this kind of measurement. In conclusion, it's not all about speed. We need consistency, and we need latency, and quality attenuation, I think, helps give us an insight into these other attributes of the quality of a broadband connection beyond just its speed. Okay, thank you.
So thanks very much, Gavin. That's a great presentation, and I know for a fact there's some fairly hairy maths behind all of that. So you've done a great job in presenting it in a straightforward and easy to understand way. Folks that are on the call, please, if you've got any questions for Gavin, please think about them and pop them into the Q&A at the bottom of the screen. And I'm sure there's quite a few questions. So I will hand over to my colleague. I think I'm handing over to George to take us through any Q&A. So George, over to you.
Well, we don't have any open questions just at the moment, Gavin. Thank you very much for that. So I'll ask you a question myself, if that's okay. That's okay. I noted from your description that you're working on fixed mobile convergence.
Yes. Yeah.
And I wanted to ask you, what sort of things are you looking at, and where will this quality attenuation help here, given the big differences that you showed in one of your slides in terms of the quality attenuation measures between, say, for example, 4G, VDSL and GPON?
Yeah, well, there's a couple of aspects to that, George. One, an obvious use case is using mobile to back up a fixed connection, which is great. I've had a couple of incidents in lockdown when my fixed line died. Fortunately, I've got a 4G SIM in my laptop, so I was able to carry on working. The rest of the family weren't quite so happy. But if that had been embedded in the broadband router, it would have carried on. And the quality attenuation angle there is sometimes you want to understand, it's not just enough to necessarily fail over to another connection. A lot of the time that will work absolutely fine, and for most things today that will be seamless. But by understanding the difference between the performance of a fixed line and the mobile connection, you can anticipate if there might be some onerous enterprise applications that somebody working from home might be using, and they don't quite work as well on the mobile line. So while they might kind of get away with it, there might be some customer dissatisfaction or frustration, and trying to tease out and understand those is something that quality attenuation can help you with. But the other one is it used to be called fixed mobile bonding, but now more commonly hybrid access, where you can actually bond the capability of the fixed and the mobile line together to give you, a higher aggregate capability. And some of the systems in that space are getting quite smart now, kind of application aware and RAN congestion aware, with very rich kind of policy capabilities. And in that situation, you may want, if you've got both a mobile and a fixed connection, you may want to have policies for certain applications that say, some applications I want to just always take the highest throughput link, or the lowest latency link, or the lowest jitter link. And so understanding the differences between 4G mobile, 5G mobile, and different fixed technologies helps us understand that whole kind of space, and what policies might be most appropriate in that situation. and that's something we've been working with vendors in that space for a while. And when you and with that kind of thing, you really do get into the details of kind of, you know, the scheduling and how it's working, and sometimes, you know, kind of packet sequencing approaches. You've got, you know, different latencies and so on. So really understanding that and being able to, you know, optimize the configuration and the scheduling in that context has been very useful for.
Thank you. That was a great answer. I'd like to encourage some of the other participants to post their questions on the Q&A, and maybe I can ask another one while we're waiting for these to emerge.
George, I was going to ask if I could ask one. It's Ian.
Yeah.
Of Gavin, because Gavin, that was great. I think way of explaining in a simplified way a very complex subject, which came across to me very well. But the issue still for me is, how do you explain it to the general public? Because I can see what you're saying about the different ways and measures, and I can see how it can be used in all of the aspects of network operations and performance monitoring and all that kind of stuff. But I still really having difficulty how you would explain it to Joe Blogs on the street, and how marketing might kind of be able to sell that quality measure as opposed to a simple speed thing. So
yeah, I think it is a real challenge here. I think, you know, in terms of just some degree of public consciousness around things like latency, I think 5G has done us a bit of a favor there. It's still not, you know, the general public aware of this, but at least the leading edge, the more tech savvy customers, you know, when 5G was developed, it was the first technology that talked about things like ultra low latency and applications for that. And some of those might be private mobile networks in warehouses, controlling robots and so on. But that need for low latency, low delay with robotics and control mechanisms, at least in the more tech savvy elements of the customer base, you know, 5G has done a bit of education on there, and similarly in the tech savvy folks on fixed broadband, you've had sites like Think Broadband, which has been, you know, a speed test site, but they've got a program, I forget what it's called now, but, you know, if you got the right, you know, type of broadband router, and it works across quite a number, then they've got a little client, and they will measure your quality, but that's basically packet loss and delay, and they give some feedback there. But that's all at the kind of leading edge of the tech savvy. A lot of folks have tried. We've seen all sorts of different people come up with typically a 5-point scale of quality of, you know, metrics, where to keep it simple for customers, there's, you know, some sort of, you know, exceptional, very good, good, bad, lousy, or whatever scale, and that maps to some sort of, you know, technical computation. Some of those linkages between the technical computation are very questionable and quite arbitrary, and there's lots of different folks who got those out there. But I think that is the challenge. How do you map that? And it's interesting, the Internet Architecture Board have got a call for papers out at the moment, and the Broadband Forum might respond to this, which is talking about this very thing. It's talking about what are the developments in measurement of broadband performance, but also it's got kind of 5 requirements there, but also it says, you know, how on earth do we come up with a metric that's useful for customers? So it'll be interesting to see, you know, what comes out of that process as well. So so I don't think there's an easy answer. Nobody's really cracked that at the moment. But yeah, I think a combination of technical and marketing folks together are going to have to come up with something there to make it tractable. But yeah, I haven't seen the perfect answer yet.
Thank you.
Jim Walmsley has just noted a thanks and a comment, discussing the potential of having quality issues despite apparently having high-speed DSL available, and this was 10 years ago. So he says it's good to see it happen. It looks really useful. He's guessing this will go a long way to address these issues, and very well presented. I'm just wondering whether the way you might be able to bring these quality attenuation measures to life for the customers would be in the context of the applications they're trying to use.
I think that's a good point, Joy. I think, you know, there are certain applications you get on your mobile phone today. You know, there's a whole range of applications for speed tests and so on, but some of them, there's one, I'm trying to think what it's called. I've got on my phone here. Is it NPerf? I think it is. Where, as well as running the traditional like speed tests and ping tests and packet loss, but it also, you know, does some application outcome tests and, you know, web surfing, Netflix, or video streaming, etc., and then translates that into a score. So people are looking at these these approaches to, you know, to see. You know, I think you're right. The application outcome, and it may be that is simplified by broken down into classes of application rather than, you know, this for Netflix, this for Amazon Prime. You know, maybe there's a streaming class, there's a surfing class, there's a collaboration, you know, VoIP, you know, class. So maybe that's an approach that could be taken there. But following on from the comment around, you know, speed problems with DSL years ago. You know, people sometimes think in this modern era, oh, I'll get myself a gigabit fiber connection and everything will be fine. You know, that's it. My problems are solved. That's not the case. I've seen this in networks. In fact, when we were working with certain suppliers and partners, where I've seen conditions where a customer has had a 1 gig symmetric connection over fiber, and yet not got the greatest, you know, speed test in the world. They've got, you know, a few hundred megabits, but it wasn't up where they thought it was going to be. And that was a real pain to dig into to understand that, because you think, well, the physical layer looks great. What's going on here? And quality attenuation enabled us to get the insight and realize that the issue in that situation was a bit like, you know, the packet buffering issue I illustrated earlier. If you've got some upstream equipment that's sending a burst of traffic, you know, I think it's something like 40 gigabits per second. Is it a 1 millisecond burst? Has got 3,000 packets of, you know, 1,500 packets. It's quite a long burst. That so just literally just a microburst can be enough to overflow the ingress buffer of downstream equipment. And if that, you know, downstream equipment then drops some packets, that will cause TCP to back off and you won't get a decent throughput in speed. Even though you've got a 1 gig connection, it's that packet layer, that scheduling mismatch. And I think in that situation, it was literally a 1 byte change in a config that fixed that, and it suddenly went from, you know, kind of mediocre to very close to the theoretical max. So that's the sort of thing that's going to make a massive difference. So, you know, going from DSL to 1 gig fiber, you'd think would be great. Well, it doesn't necessarily mean your world's going to be perfect if you don't understand the packet layer performance. You know, and it's the same with Wi-Fi. There's fantastic developments in Wi-Fi with mesh systems. You know, multiple access points to give you coverage. There's Wi-Fi 6 and 6E. In a couple of years, 3 years, we might have Wi-Fi 7. So the speed of Wi-Fi, the spectrum available, the coverage in your home, we can address those physical layer issues. But again, if you don't get the packet layer right, you know, you can still have a lousy application outcome, which at the end of the day, what customers care about is their application outcomes. I mean, some of them might want to boast about having the best speed test in the village, but reality is it's the applications that you're using, particularly if, you know, those of us stuck in front of a laptop all day in lockdown using it too many hours a day, you just want that to do exactly as you expect. You don't want glitches and buffering and, you know, dropouts.
So given that we don't have any direct questions, I'd like to encourage them again, the participants to contribute some questions if you can. But on application outcomes, I recall once in the voice days that one of the US long distance carriers had the pin drop network, and so that was an indication of the you know, the voice quality that you could expect over their long distance line, but it was very much an application specific marketing message that they were giving linked to the quality of their network. So if you had that kind of thing across a range of applications, which could be video streaming, channel hopping, you know, Zoom calling or whatever, how how could you overcome some concerns about net neutrality? Because inevitably this would be putting in place some kind of traffic management. How could you overcome some concerns about net neutrality in that context?
Yeah, I think yeah, net neutrality is always one of those kind of contentious issues. I think, you know, one way around some of these challenges with net neutrality is to put the control in the hands of the customer. You know, and I've seen this develop, whether it's, you know, a kind of Wi-Fi capability or a, you know, hybrid access or whatever, given the customer the ability to decide themselves which applications they would like, you know, prioritize, for example, across their Wi-Fi. You know, you know, we had this discussion, and I nearly got my head bitten off in an internal discussion once, because, you know, your natural assumption was, oh, people working from home, that's a higher priority than gaming, and, you know, if my son's on his Xbox, I don't want that prioritized. But then somebody picked up and said, what if you're a professional gamer and that's your livelihood? I thought, yeah, I didn't think of that. So it's not necessarily the right thing for network or service providers to assume they understand what the priority should be. And if you can give that control in the hands of the customer to, you know, and I know folks are working on this on Wi-Fi and other systems, that that can be through a simple portal or an app that basically sets the policy. If the customer's in control and it's their choice, then I think that helps you get around a number of the issues.
Can I encourage some additional questions from any audience members, any participants? Can I ask our chairman potentially to ask one?
Thank you. Thank you, George. Gavin, I know you've put a lot of effort into this in the broadband forum to standardize the probes and the capabilities. To what extent are vendors incorporating the necessary agents in here to do an end-to-end assessment?
Yeah, that's definitely starting to happen. It's been very interesting seeing which vendors get this quickly and which don't, and it takes them several months. You know, we've seen some vendors literally get this and be able to build prototypes within, you know, within 4 weeks, which is fantastic, and others, you know, have taken several months before the pennies dropped. And it's actually, you know, and actually it spans across different vendor types. So there are some test equipment vendors, you know, people who make probes and lab test equipment, and we've seen some very you know, interesting and you know, really good looking developments in that space. And in some ways you'd expect that, because they're the folks who are familiar with cumulative distribution functions and latency and TWAMP type protocols, etc. So that's interesting. I mentioned, you know, Domos and the Wi-Fi context. That was really imaginative how that's been coupled with machine learning. We're also seeing some traditional equipment vendors looking at this as well, and some folks have done demonstrations at the BBF organizes demonstrations of its work sometimes at the Broadband World Forum, and before lockdown, I think the last Broadband World Forum before lockdown, and Vodafone with Predictable Network Solutions and Outsys and others work together to demonstrate some capabilities in this area. There are CPE vendors that are working on aspects of this, and even chipset vendors. I can't mention any names, but there's certainly at least 3 key chipset vendors that have been looking at this, and some modern packet processing silicon has already got various, you know, telemetry and IP performance metrics, and folks are looking at, well, have they got the basic hooks there that they can tweak a little bit to do this? So so that vision I painted of having this at every hop, you know, that something like that is never a quick win. It's going to take a while to get that into the ecosystem. But what helps us a lot is the fact that increasingly networks are built from software and not hardware. So, you know, you don't need to wait for 3 years for somebody to, you know, get this into silicon, that as people instantiate virtual and containerized network functions, they can implement this kind of thing in software. You have to think about, you know, the rate at which you're doing measurements and how you're storing and gathering data, and there's certain things that you might want to measure and act on locally quickly, some kind of closed loop automation perhaps based on these measurements, but then you can aggregate some of the results and summarize them and send them northbound to, say, a data lake in the cloud for something that's more to do with, say, trend analysis or capacity management or understanding things. So there's some work we put into the broadband forum around closed loop automation and hierarchical approaches to this, and the same thing, and that's generic across a lot of telemetry, but the same sort of thing can be applied to these kind of measurements. You know, there's a local use to close a loop and act quickly, and then there's a kind of more centralized, you know, use cases. But as I say, once you're implementing network functions in software, it becomes easier, and some folks have implemented this very quickly indeed.
Right, as we've no open questions, thank you very much for answering those so well, Gavin. I want to pass you back to Kevin, our chairman. I can't do that, he's disappeared. Oh well, right. Well, in that case, what I will do then is, what I'd like to do is to thank you, Gavin, on behalf of the IET Anglian Local Network for giving us an excellent presentation. And what I'd like to do is to note that we have some further presentations coming up. I don't know, Ian, if you're able to find the slides that we would normally put up.
Probably not that quickly, but I can tell you what the next presentation is on behalf of Kevin, and that's a presentation given by a chap called David Smith, and it's going to be on the project of bringing a Mosquito, which was an RAF fighter, back to flying in the UK skies. And basically it's the project which found about 22,000 engineering drawings before they were just about to be thrown away. And this particular group of people are trying to build up the Mosquito from those engineering drawings, because if they can, it gets CAA compliance apparently, so they'll be able to fly it. So the presentation is hearing that story. And that's on Wednesday the 7th next week, and it's at 7 p.m.
Okay, so in that case, what I'd like to do is to bring the meeting to an end. Thank you very much indeed, Gavin, for an excellent presentation. Sorry, we've just had a little bit of a glitch with our chairman disappearing. Just
no problem. Well, he'll show up somewhere.
I'm sure.
And thanks for the invite. Appreciate it.
Yes, thank you. Thank you very much indeed. Bye-bye then.
Thank you.
Thank you,
Bye.
Gavin.
Thank you. Bye.